Hello. Uh, so right now we're going to talk about a specific type of graph. This is a discrete time model, and this can be used to model changes in biological populations. So first of all, this is the equation of this line, which looks like an upside down parabola. So first of all, the output of this graph is t plus 1. What does t plus 1 mean? Well, you first need to understand what t means. T is a period of time. Let's say 1 year. If t is a specific year, let's say 2001, t plus 1 is the next year, 2002. So what this graph tells you is if you know the size of a population in a particular year, you can input that value into this equation and get the output of the next year. So if I know the population in 2001, I get the output, which is the population in 2002. So remember that keep in mind that Desmos won't really like equations like this, written like this. It won't recognize what t sub plus 1 means. So you'll have to write it in like this as some function of x. But these two equations mean the exact same thing. X is the input and t of x is the output. So if we want to find specific answers to this equation, instead of hovering over the line with the cursor like this, which can be kind of hard to pinpoint exact values, you can instead write an equation for a line and find the intersection of that line with the parabola. So for example, if we know the population of 2001 to be 500, we want to find out what the population in 2002 would be. We can write the equation x equals 500 and make a vertical line, and that will intersect the parabola right here. So we get an exact value. When the population in 2001 is 500, the population in 2002 is 1,500. Likewise, we can find what inputs will result in specific outputs. So for example, if I want to know that what size of population I need right now to have a population of 1,000 the next year, I can write the equation y equals 1,000 and find the intersections here. One of the answers is 292.893, and the other answer is 1,707. Now, the properties of this parabola are quite interesting, and that's what makes it very useful for studying biological populations. As you can see here, when the population is small, like 300, the next year's population will be bigger, like 1,000. Likewise, when the current population is big, the next year's population will be smaller. And that's why this is so good at modeling biological populations. When in real life, when there's too many plants or animals crowded in one space, there'll be too many resources. Some animals and plants will die, and the next year's population will be smaller. But if there's an abundance of resources and there's a small population, that small population will grow the next year and have a larger population. But somewhere in the middle, there will be a point when the population will not change, and that is called the carrying capacity. And I will leave it up to you to find how you would find the carrying capacity from this graph. Remember, it's when the population will no longer fluctuate. Speaking of fluctuations, you can use this graph recursively to find populations beyond the first year. What that means is you can use the outputs of this function and reuse them as the inputs. An example of that would be if I know the population of 2001, but I want to find the population of 2003. Means what I would do is, first of all, let's say the population of 2001 is 200. 200. That means the population next year will be 720. And so I would use 720 as the new input. And that's the population of the next year and 2 years after that. And that would give me 1,843. That's pretty much all you need to know for your escape room task, and good luck.